We're looking at 9.1. And like I said on the previous video, we are moving a little bit away from talking about trig functions. They will come up again in this chapter, but like I said, very little, like in the previous section. But to build off that idea with parametric equations of talking about this direction, we introduce vectors, which have to do with very important part of a vector, its direction. So let's start off with the definition. So it's a line segment with direction and magnitude. I usually have a short video from, I think it's Despicable Me. If anyone has seen it, you guys can look it up, where it has the villain Vector, and he says that something about him being a villain with direction and magnitude, taking over the world or something with direction and magnitude. But if you want to watch it, look it up. I don't have it set up for the video. Now, like I said, these are very key points. It's direction and magnitude. Now, the quickest way to think about a vector is think about a force in real life, right? When you push or pull or pick up something, there's these forces that are acting on each object. There's even a force acting on us, the force of gravity. And all these forces can be represented as a vector. And again, they're line. Now, we can't see them, right? But we can definitely feel them. And feeling something is not only its direction, but sometimes feeling the strength, right? There's a big difference between you tapping someone on the shoulder versus shoving someone from the shoulder, right? Like one has, you can definitely feel that pressure, right? But in math, I can't illustrate that force. I can't illustrate that magnitude, right? So that would be illustrated with the length of the line segment. And then it's really important. There's the huge difference between a push and a pull. You can push with the same force and pull with the same force, but those are two very different directions. That's why not only is the direction important, not only the magnitude is important, but the direction as well. So there's a huge difference between pull and push, but their magnitudes can be the same. But the direction is definitely different. And the way we're going to illustrate these forces or these vectors is with a line. And this is what it's going to look like. So I'll just sketch one real quickly. So if you notice, it's a line segment, meaning there's this start and end, and we will describe that. And one thing that I'm not describing is the position. So I did say, I keep doing the same mistake. I did say there is a difference between the magnitude and direction. They're both important. But something I didn't say is the position doesn't matter, right? So all these vectors I'm sketching here, if you notice, I copied one and then wrote all of them. Just copied and started pasting them everywhere on the graph. Now, all these vectors are essentially the exact same, right? The difference between you pushing a table from the middle of the room, or the table being on the side of the room or in the corner of a room, or pulling it. Now, the pulling will have a different direction, but if you push, it doesn't matter what. Let's say you're in a room, it doesn't matter where this table is positioned. If you want to move it in a specific direction, you need the exact same magnitude, same direction, and it doesn't matter the position of where this table is in a room, but the direction that you're pushing and how hard you're pushing, right? The direction and magnitude are important. Now let me give you what some of the notation is going to be for these vectors. Now I do have the example written out. So sometimes vectors are denoted with like V, W, M, N, and sometimes they're just in bold. They can also have U, V, W is usually letters that are used, right? The same way X, Y, Z are used for vectors. And then, X, Y, Z are used for variables. A, B, C are used for constants. F, H, F, G, and H are used for function notation. So there's always these historically particular letters in the alphabet that pertain to certain topics in mathematics. So here's another notation using these inequality symbols. And then we're going to have this I, J, K, which we'll get further into that. But the idea is all these can be written in this form in some way. Either say it's vector V, or these are going to be considered introducing the components, which we'll talk about that shortly. But remember, the position doesn't matter, but the direction and magnitude do. And in terms of showing this on a graph, when we say magnitude, we're talking about the length, right? And the way to represent it is to represent a stronger force, we draw a longer line, right? The direction is then determined by this arrow, right? This could be more of a push direction. If I put the arrow on the opposite side, that could be more of a pulling direction if we thought about this in real life. Now, even though all these are the exact same vector, and you saw me copy and paste them, this vector here has a special name to it. And that name is known as the representation vector. Maybe I should denote that differently. So this is known as the representation vector. And what makes it the representation vector? It's solely because the initial point, and I'll talk about what that means. So representation vector has the initial point, like I just said, has initial point on the origin. So here is, this is my initial point, right? Because we have to, if direction is important, we have to know if this was pointing in this direction or versus pointing in that upward direction. And that's determined by the initial point. And then there's also the terminal point, kind of telling you the tip, I guess. The tip of the vector. And it's a representation vector because the initial point, like how it says there, the initial point is at the origin. And it's nice to have it at the origin just because it really helps describe or visualize the component of the vector. Now, what do I mean by components? So we'll move to this next problem definition. So again, these vectors, these forces, we're trying to sketch them in a two-dimensional graph. And to bring these into more math and algebra versus the real world and things in 3D, which we will talk about 3D as well, we have, when we think about 2D, we think about the X, Y axis. So we have to place these on this graph. Like I said, we have an initial point. Now the representation vector is at the origin, which the origin is where X is 0 and Y is 0. But that doesn't mean, right? We said the position can be anywhere. So all these points have a slightly different initial point, slightly different terminal point. But the components for all of these will be exactly the same. Again, because the position doesn't matter, but the direction and magnitude does. So again, this initial and terminal point are just establishing the position. But I want to be able to find the components because that's the most important part. Now, dealing with lines, all you're essentially doing to these points is finding the change in X and the change in Y. Now, we did something similar to this in algebra when you found the slope of a line. It was a change in X over the change in Y. But here, we're not describing it as a slope. We're describing the direction. And we're writing each direction individually. The reason why I bring that up is because in algebra, it didn't matter where the initial or terminal point was. You just found the change in X over the change in Y. But here, we have to be really careful in terms of where's our initial and our terminal point. Because we have to make sure we subtract them. Terminal minus initial. So in physics, there's a phrase that says final minus initial. That's how I always remembered it. Same thing for the X components and the Y components. So that's going to be so we'll take the initial point, and I don't care if you remember if it's P or Q, but you do need to remember that it's known as an initial point and a terminal point. Let me write this in caps. So, to do this example, there's a reason why I have it in blue, and that's to illustrate why the representation vector is nice, but we'll do this after. But here, it's pretty quick, right? Let's just call this vector V. I'm going to take the x coordinate of the terminal point, which is 3. Then you want to be careful because I'm going to subtract by the x coordinate of the initial point. But the initial point is a negative number already. So you have to watch out for these negatives can make positive. A common error teachers make is to not overemphasize how there's already subtraction in your formula and then there's a negative number. Don't ever just write 3 minus 2 thinking that the negative from the number is the same negative as the subtraction. So watch out for those little details. Sorry. Now we have to do the x component, so it's a y component, 7 minus 5. And that's going to simplify to 3 plus 2 is going to give me 5. And 7 minus 5 is going to give me 2. And if you want to pause to try the next example, you're more than welcome to. But I'll just continue. So it's going to be 2 minus 4. And then 3 minus 1 for the y components. And that's going to give me the vector -2 and +2. And this is why it's very important that you don't switch the terminal with the initial. Because if you were to subtract in the wrong order, you would have 4 minus 2, which would be a +2. Now, for a linear equation, finding the slope, that didn't matter because in slope formula, you either have the negative in the numerator or the negative in the denominator, because it was a change in x divided by the change in y. But that didn't make a difference, because a positive divided by a negative is still negative, and a negative divided by a positive is still positive for a slope formula. But here, this matters because one might face upward and the other one might end up facing downward. Now, this doesn't change the length, but it does change the direction if you want to subtract in the correct order. So make sure you keep that in mind. Now, it's tricky to make the connection between this initial and terminal point with the component form of the vector. Because how do these 2 points correspond to these vectors? Well, I have a representation here of this particular vector. So here's my point -2 and 5, and my point 3 and 7. Because I know -2 and 5 is the initial point, I know that my vector is in this direction. Now, the 5 and 2 speaks to how it changes 5 in the x direction and 2 in the y direction. Very similar to what slope would look like. But we start initial, go positive, and then up. That's how we know the arrow's pointing in this direction versus the opposite direction. Right? Or even it might have the same magnitude, but it could be pointing something completely different. Because if we got -5, it would be, and 2, the direction will be completely different. That's why it's important to keep that order. You might switch the direction around, or you can have a completely different direction. So it's important to keep that terminal and initial separate. Now, the reason why the representation vector is nice is because it does help see, right? I just copied this. And my graph isn't perfect, but it does help me see how the representation, at least. So 1, 2, 3, 4, 5, and then 1 and 2. So here's a 5, here's a 1. Again, these two are exactly the same. Of course, I'm sketching this by hand, so it might not be perfect. Right, I can kind of take this one and hover it over. And if you notice, I'm off a little bit just because of how I did my scale, but that's pretty much the exact same vector. But as as a representation vector, I can see the 5, right, on the x and then the 2 on the y. That's what's nice about it, but that doesn't mean I can't just, again, I can start at any position and get the vector as well. But the representation is nice because it's visually a little more pleasing, and maybe the components 5 and 2, it's much nicer to comprehend, being able to see that. But again, they're the exact same thing. Now that just speaks to one, getting the components and thinking about its direction, right? But now we have to talk about its magnitude, right? The magnitude of the vector. But let's not forget, there's no way we can illustrate magnitude on 2 dimensions, right? Like a force, but we can illustrate its length. Now, something that we can pull from our previous section is, if you look at this representation vector, well, it sure looks like a right triangle, right? And the magnitude of this vector is the length of it, which, if you look at this right triangle, that just looks like the hypotenuse. So how would I find the length? Well, we have to remember a squared plus b squared equals the hypotenuse squared, which I can find the hypotenuse by just doing the square root property, right? Now, normally you have to add plus or minus for a square root property, but since this pertains to a length, every magnitude that I do is going to have a positive. So the magnitude or length of a vector let's say vector v, so it has a sub 1, a sub 2, so that x and y component, or some people say a or b, right, will give us, let me fix this a little bit so I can fit everything better. And this is the notation. So the notation of a vector uses these absolute value symbols. One, because if you remember from algebra, absolute value does mean length. So it is appropriate to maybe use that notation. In some books, they use double lines, right, to not mix up absolute value with the magnitude of a vector. But in this book, we use just the single bars. And this is what the magnitude is, right? It's just taking the square of both legs. If this, we saw we can create a triangle from it, we're essentially just getting the hypotenuse. So here, like I said, this is pretty straightforward. So finding the magnitude of vector, and sometimes eventually I'll probably drop the little arrow above, but for now it's nice to get used to it. It's just going to be the square root of 2 squared plus negative 3 squared. That's going to give us the square root of 4 plus 9 is just going to be square root of 13. Next example, we'll have the square root of, here, magnitude of v. I forgot to, my eyes were getting mixed up. So the magnitude is 5 squared plus 0 squared. That's just going to be the square root of 25, which is just 5. And lastly, vector w, the magnitude is the square root of 14 squared plus 3 squared. Sorry, I didn't say 4 squared, not cubed. I don't know why I wrote that. It's going to be 16 plus 9 is equal to the square root of 25, which is going to give us 5. Now that illustrates something important, because that means these two vectors have the same magnitude, but their direction is different. Going back to what makes a vector unique, its direction and magnitude, not necessarily its position. Now, what else can we do with these vectors? Right now that we can see its components, understanding its direction, understanding its magnitude, well, we have to first establish its algebraic operations. Like when you first learned about numbers and polynomials, you had to learn how to add, subtract, multiply, divide. Well, we're going to do the same with these vectors, trying to understand how does multiplication, addition, subtraction, how does that play a role with a vector? Now, they're not all going to be, it's not going to be all exactly how, even though this might almost look like a binomial, some things might be similar to polynomials, but they are clearly different. And the geometric behavior, which I'll show, is going to be different as well. So if we have these two vectors u and v, if you try to see how much room we have, if you try to add these two vectors together, it's pretty straightforward. All you do is take the x component of u, add it with the x component of v, and that gives you a new x component, and then you're going to do the same for the y component portion. You're just going to add the corresponding components to each other. So here now we'll maybe highlight with color to help emphasize this a little bit. So you have to do the corresponding vectors, and then subtraction. It's going to work the exact same way. You just subtract the corresponding components. But of course, if that component is negative, make sure you are careful when you are applying that subtraction. And there is this scalar multiplication. Now, multiplying two vectors together is going to have a slightly different representation, and that's going to be in our next section. But for now, we're still focusing on our components, and this is going to resemble more of a distribution where you take each component and you multiply it by a scalar. So this is known as scalar multiplication. So we have addition, subtraction, and multiplication, but a very specific multiplication. Not a multiplication between two vectors, but this scalar. And the idea, right, if we go back to our polar equations, we saw how the petals or the cardioids would get larger and smaller, and that would get larger and smaller. by this number. Now, like I said, how do I represent the magnitude? We have a length. But what's the difference between a tap on the shoulder versus a shove on the shoulder? Physically, we know that feeling. There's definitely a difference. But algebraically, to represent that is maybe a tap on the shoulder is this little arrow. A shove is a much longer arrow, right? A much larger magnitude. So that's what this is going to help with. Now, let's apply these operations with these two vectors. So we're going to take the vectors. So like I said, take the x component, which is going to be 2, and then add it, since we're adding, with the negative 1. And then we have negative 3 with v, so plus 2. And that leaves us with, so the sum of two vectors leaves us with a new vector 1 comma negative 1. Now just like for the components, right, when we're looking at 2 points, you want to do terminal minus initial. Here you want to add in the order that's given. So we do the same thing for subtraction. We take the x component of u, subtract it with the x component of v. But like I said before, I am not mixing up the negative in the component with the subtraction of the operation, or the operation subtraction. And then I have, once again, negative 3 minus 2, which is going to give us, right, these two negatives become positive. It's going to give us 3 and negative 5. And this next one involves a scalar multiplication. So I'm going to do this one in 2 parts. 1, so 2u. So 2u is taking 2 times 2, right? I'm multiplying the x component of u, and then 2 times the y component of u, and then it's subtracting. Now you can do 2 different things here. You can either distribute, for lack of a better word, we can distribute negative 3, or you can just distribute 3 itself. So let me move this a little bit to make room for that distribution. Or you can leave the negative out and just distribute the 3. Either way works. Or you can multiply by negative 3 and then just add them together, whichever you prefer. But that's going to leave us with 4 from u minus negative 3 from v. And then we have negative 6 minus 6, which will leave us with the vector. Again, these 2 negatives become a positive. That's going to be 7. Those 2 negatives become more negative and gives us negative 12. And you can work them out if you like. But again, the operations are pretty straightforward, very algebraic, not too difficult. Now, just something I want to illustrate is what's truly happening in this sum. Like, why do we just add the x and y components to each other? And that's because when you take the vector u, and let's just make up this random vector here. Let's call this vector u. Let's say we take vector v. Oops. Vector v. And I add them together. Geometrically, the way you add the vectors together is you have to take the initial point of v So we're adding in this order, right? Where v is adding onto u. So we're going to take the initial point of v and put it on, and sorry for the lack of a better wording, put it on terminal point of u. Sort of and these aren't actual steps. I'm just trying to break it down to make sense. And the sum of the vectors, so I say the sum is the vector from initial point. It's a very long explanation, but the sum of the vectors, the sum is a vector from initial point v and terminal point u. No, sorry, it's backwards. It's from initial point u, and once we draw it, it's going to make sense. The wording might be a little confusing because we start with initial point v, and then we put it on terminal point u, and then we look at the initial point of u and the terminal point of v. But this is how it's going to look. I'm going to copy this vector, right? This is vector u, and I'm going to copy vector v. So, oops, paste it. So here's a vector, and this is what I mean about put it. I'm taking the initial point, right, the back end, and I'm putting it on the terminal point. I actually needed to make more room. So let me move this down here. I'm going to take the initial point of v, and I put it, right here. We have the initial point of v, and then we have the terminal point of u. Now the vector that has been created, I'm going to move this part out of the way, is we have to go, or I'll leave it there. We have to go from the initial point of u now and go to the terminal point. I'm going to zoom in here. So we went from initial point of u to terminal point of v. And this is the vector u plus v. And that's what's going on here between these vectors. We're taking the x component of each one of them, and we're adding them together. we're taking then the y component of each, and we're adding them together. And you can see that a little bit, right? Because this is the y component for u, this is a y component for v. Putting that together definitely makes it much longer. And that's what's happening geometrically with these graphs. And now the scalar, again, this just scales a vector. And naturally, we always think about scaling to make things larger, but it does a little bit more than that geometrically. So once again, let's take this same vector, copy vector u. Now, I can multiply that vector, right, by 2, and what that creates is, I'm going to move this part, and there's 2 of them. This is what 2u really means. I doubled the length of the vector, right? And then what does it mean when we multiply by a negative? Well, it takes the exact same vector. Now the only difference is that it changes the direction. This is what it would mean to be a negative u. And change the color because that's previous one. We'll do purple. But that's what it means to scale the vector. You can either scale it larger. Let me move this one here. I'll put this one there. So you can double the length. You can even shrink the vector, right? I can multiply the vector by half. That means I'll take half of that length. The negative is just changes the direction. Numbers bigger than 1 just make it much longer. And again, this is what's happening for these different operations, right? Adding, subtracting, multiplying, and dividing. Now, since to not make this video really long, I am going to end it here. And the next portion of this will talk about this notation of the vector, this I and j, and writing it in slightly different notations. And we can introduce a little bit of another notation that involves cosine and sine. And then we'll move on to what does the multiplication between two vectors looks like versus this scalar multiplication, a slightly different type of multiplication. And that's going to be known as a dot product. But that's going to be our 9.2. And then we'll talk about all these exact same ideas. So finding the components, thinking about the direction, finding its magnitude, doing these operations, all in 3 dimensions. And all those are, be the exact same thing, just adding one more component to these vectors. That's all 3-dimensional. All 3 dimensions will do. Okay, but I'll end this here. And our exam will be up to 9.1.